Good day. We're back. In another module, we spoke about the problem of standardization of units as ways of measuring certain quantities. And I spoke about the plethora of different unit systems that has evolved in Western Europe over the course of its history. And the confusion that results from having multiple systems of units with complicated ways of converting measurements in one system of units to measurements in another system of units. Now, this confusion has led to a desire amongst people who live by numbers, not only people who are involved in trade, but people who are interested in studying nature, systems of simple and easily comprehensible units that can provide measurements that everyone agrees upon. And what I'd like to do in this module is to outline a little bit of the history of this effort and to introduce what is now the current standard for units of measurement in scientific endeavors. Now, I mentioned in another module that the Anglo-Saxon and the Roman traditions had different means of multiplying quantities. Anglo-Saxon preferred multiples of 3, whereas Romans preferred multiples of 5 and 10. And you can see some of this in certain aspects of our current calendar, for example. If the original Roman calendar had only 10 months, not 12 months as ours does. And you can see this reflected in some of the names of the months. September, for example, is the 7th month. October is the 8th month. November is the 9th month, and December is the 10th month. December, deci meaning 10, novo meaning 9, and so forth. Of course, when the Caesars came into power, they introduced two new months to be able to honor them. That's where our months of July and August come from. But the original Roman calendar had only 10 months in it. Now, in scientific endeavors, multiplying by powers of 10 is much easier to do than multiplying by multiples of 3. So, for example, a mile has 1,000 steps, but in the case of an English system, a mile consists of 5,280 feet. Which conversion would you rather remember, 1,000 or 5,280? Excuse me. And so one of the things that has driven standardization of units is to try to quantify them so that you can have easy factors of conversion from one to another. And another drive has been to identify what is it that we are actually measuring, and this is where the relationship to dimensions comes in. And so in science, what you have had is the development of systems of units that are based upon certain fundamental dimensions and that are measured in quantities that can be specified as multiples of 10. Now, the French, during the French Revolution, decided that it would be useful to go back to this Roman system as much as possible. In fact, the French calendar, before they came to their senses, reverted to a 10-month calendar for a time, but eventually they decided that it was prudent to go along with the rest of Europe and readopted the 12-month calendar. But among the things that the French did in this drive to impose a base 10 type of system on units of measurements was to develop what we now know as the metric system. And the metric system takes these fundamental quantities of nature, in particular the three mechanical dimensions of length, mass, and time, and to quantify them in units that are multiples of 10 of one another. So, for example, if you take the simple dimension of length, the standard measure of length in the metric system is the meter. And the meter is defined as a particular standard length. For a long time it was defined as a length of a rod of platinum and iridium kept in a vault in Paris. We have different measures, different standard measures of the meter right now, but the meter stands as the fundamental unit of length in this system. You can describe different subdivisions or different multiples of the unit of meter. So, for example, we can refer to as a shorter length as a centimeter. This is simply 1/100th of a meter. Again, that's divisible by a power of 10. You can refer to an even shorter length as a millimeter. This is 1/1000th of a meter. And you can talk about larger measures. Sorry, I'm about to write kilogram here. You can talk about larger lengths. Let's get rid of this. Let's write it properly. The kilometer, for example, is 1,000 meters. And again, we have a multiple of 10 operating here. Now, scientists, beginning back at the end of the 18th century, 1799 or so, sought to standardize this in terms of the fundamental dimensions of matter and the universe. And so, what they did was they defined a particular set of measurements. We've already spoken about the dimension of length, that is the meter. In terms of the unit of mass, the dimension of mass, that is the gram. And the unit of time, the dimension of time, is the second. Now, for various interesting reasons in the history of science, some of the first people to actually start using these systems of units as scientific tools, individuals like Antoine Lavoisier. Sorry, I think we're going to have to cut that. If you look at the history of the use of these units, the original French scientists like Antoine Lavoisier, who measured metabolic rates of animals, for example, units of meters for length was a little bit inconvenient for them. And so what this transmogrified into was that the fundamental unit was actually 1/100th of a meter. That was just a more convenient system to use. The gram stayed as the unit of mass. That was also a convenient unit to use. And the second stayed as the unit of time. And this led to the first traditional quantification of units in the metric system, called the so-called CGS system. And CGS simply refers to centimeters, grams, seconds, the units of the fundamental mechanical properties of matter, length, mass, and time. But scientists are just as contentious as merchants are, and for some scientists, the CGS system was not really all that convenient, and so there was a bit of clamoring for other units, and this took place through the 19th century, and finally in the 20th century, scientists agreed on a modification of the CGS system. And in this case, what we refer to there, we keep the meter as the basic unit, but that's not very convenient for people who are trying to measure things like diameters of planets or distances of stars and those kinds of things. But it's more convenient than the centimeter was. Again, the gram was not all that convenient, and so what these scientists agreed upon was that instead of the gram, the kilogram would be the standard unit of mass, and then time, seconds, that was okay. So they kept the second unit of time. And this system of mechanical units, rather than centimeters, grams, and seconds, we use meters, kilograms, and seconds. This led to the kilogram, meter, second system, which forms the foundation of our modern system of units. And this was basically in place by the beginning of the 20th century. Now, various other kinds of considerations have always entered into the need to agree on systems of units, and so there's been a series of meetings that have taken place over the course of the 20th century. These take place on the order of once every decade or so in Paris. And there have been various tweaks and modifications of the kilogram meter second system of units, and the current system is known by its French name, and that is known as the SI system, and this is in French. I'm not going to attempt to pronounce it, but this is the standard unit or system of units that we now refer to, and it's usually referred to as the SI system by English speakers. Of course, SI system is redundant because the word system is already in there. Now, there are certain rules for using SI units. And what I'd like to do is just to go through some of those. And one of the first things that we have to realize about SI units is that it is expanded to meet the needs of physicists who are dealing with different kinds of fields. And so, for example, a kilogram meter per second kilogram meter and second are fine as fundamental units, but we also have to agree upon different people who are studying different things have other kinds of considerations that they're looking at. So, for example, if you are talking about chemists, they have to measure quantities of atoms, quantities of molecules, and so forth, and these come in whole number units. And so you have to have a standard unit for quantity, and because chemists have demanded this, the standard SI unit for quantity is the mole, MOL, abbreviated MOL, and that, of course, simply refers to Avogadro's number of particles, 6.02 times 10 to the 23rd. On the other hand, people who are interested in electricity and magnetism, they want to be able to quantify flows of electrons and those sorts of things. And so what they have done is incorporate an SI unit for current, and the SI unit for current is the ampere. 1 coulomb per second of flow of electrons, and a coulomb is simply a mole of electrons. Different considerations also come in, because if you're dealing with thermodynamic types of issues, you have to be able to measure temperature very precisely. And so there's a fundamental SI unit for temperature, and that's usually abbreviated as a capital letter TAW, T-A-W. It looks kind of like a scrunched up capital Y. And the unit of temperature is the Kelvin, named after Lord Kelvin. And then finally, people who study light want to have their own SI unit, and this is like electrical current, but it refers to flows of photons rather than electrons. And sorry, I meant to write that differently. That's a lambda. Let's cross that out. That's a lambda for light, and the standard unit for that is the candela, which is the flux of a mole of photons across a meter squared of area. And so if you look at the modern SI system of units, it has gone beyond the basic mechanical units that we spoke about earlier to include other kinds of quantities that are important to measure in physics. And there are 7 agreed upon standards of 7 agreed upon basic units of these quantities. Another thing that the SI system does for us is it gives us a rational way of expressing multiples or divisions of these particular units. And we start off with a so-called base unit, and let's just deal with the meter, for example, as our base unit. The meter can be written as a number times 10 to the 0 power, and of course 10 to anything to the 0 power is 1. And so if you have 1 meter, for example, that's the same as 1 times 10 to the 0 meter, and what you end up with, again, of course, is just 1 meter. But suppose you want to measure a kilometer. Well, a kilometer is simply the measure times 10 to the third. All right? And if we wanted to define a shorter measure, we could talk about a millimeter. That's millimeters times 10 to the minus third. Or a micrometer, which is meters times 10 to the minus sixth. Or a nanometer, which is meters times 10 to the minus 9, and so forth. Now, the SI system recognizes divisions like this. They're all in exponents, or 10 raised to exponents and multiples of 3. Minus 3, minus 6, minus 9, 3, 6, 9, and so forth, all the way up to 10 to the 24th power on the large side, and 10 to the minus 24th power on the low side. And if you want to look up what these designators are, then there's an essay that is available on the web that will let you quantify those. But these basic multipliers right here refer to any kind of multiplication. So, for example, kilo is the multiplier for anything times 1,000. And so you have 1,000 kilometers. But if you have 10 to the 6th, that refers to that goes by the name of mega, and that's abbreviated as a capital M, followed by the small m, which indicates meters. We often don't talk about megameters. That's a bit awkward. But this continues to go up and up and up in multiples of 3. Okay. Now, as we mentioned in our discussion of dimensions, you can use the rules for calculating derived dimensions and apply those to calculating derived units as well. So, for example, in SI terminology, the basic unit of the area is the meter squared. The basic unit of volume is the meter cubed. The basic unit of density is kilograms, that's the standard, per meter cubed. And again, the SI terminology abjures quotients. So instead of writing this as kilograms / meter cubed, what we do is we refer to this as kilograms times meter to the minus third power. Same thing with speed. Meters per second is the appropriate SI designation of this. But what we do is we now put the S on the same line, and we refer to speed as the product of meters times seconds to the minus 1, or 1 over a second. Again, let's just continue what we were outlining with dimensions. Acceleration is a change of speed with respect to time, and now the units SI designation for that is meters times seconds to the minus 2, and so forth. And we'll have occasion to refer to different kinds of derived units as for pressure or force or work or any of those kinds of things when we come back. Okay, so that's all for now, and we will come back to another part of this discussion in the next module.